Hi, this video is for my CPE or CP class. What I'm going to talk about now is just putting something on a ramp, because we haven't done that so far. So in the past, what we had objects moving on a flat surface, right? And we pulled them at a constant speed. We accelerated them. We pulled them parallel to the surface. We pulled them at an angle to the surface. We pushed them at an angle. We did a lot of things. Now what I'm going to do is that I'm going to take an object and I'm going to put it on the ramp. So I can either let it slide on the ramp, let it just rest on the ramp. We're going to look at the Newton's second law for all of these cases. I can push it up the ramp. Okay. One thing I'm not going to do, I can pull it up the ramp. One thing I'm not going to do, I'm not going to pull it at an angle on the ramp. It just becomes a little too complicated. So let's think about this conceptually first. Let's look at the forces acting on this. And I'm going to concentrate mainly on 2 or 3 forces. I'm going to concentrate on the weight, and I'm going to concentrate on the normal force. When it's sitting like this on a flat surface, whether I'm pulling it or pushing it, not on an angle parallel to the surface, the Fg, or the force of gravity, is equal to the normal force. Okay? Now, the normal force, keep this in mind, the normal force is basically how much support you're getting from the board, right? So basically, if I try to lift this brick up and it doesn't leave the surface, I can say that the normal force is less than the mg, because it's not just the board that's supporting the brick, but I'm also lifting the brick up in the air, right? Or trying to. It's not coming up. Let me just make sure we're recording. Yeah, okay. If I'm pushing down on the brick, now the board or the table has to support more than just the weight of the brick. It has to support the weight of the brick and the amount of push that my hand is providing, okay? Now, so basically I can say that the normal force has to do with how tight the surface is, or the contact is. So if I'm trying to lift, I'm weakening the contact between the brick and the surface here. If I'm pushing, I'm making the contact stronger. So let's think about that. If I raise the board like this, conceptually, we should see, and we'll prove this with the math, conceptually you should see that the normal force has to be less. In other words, that contact is weaker, right? If I do this, the contact has to get weaker. Okay, so the normal force decreases as we increase the angle. Okay, now there is another force that comes into play, and that's trying to make the object slide down the ramp. So if I raise the board like this, it doesn't slide because there is got to be some friction holding it up. Okay, if I increase the angle, that tendency to slide increases, and the force of friction has to increase also, because this is at rest. And I'm talking about on the ramp. I'm looking at the ramp as my x-axis, in other words, right? If I keep increasing, the tendency gets higher, right? And this tendency has to have something to do with the force of gravity, okay? All right, so we're going to do that mathematically. So now, in the past, we had our x and y axis like this. Now, all we're going to do now is that we're going to tilt everything. So we're going to tilt here, and we're going to tilt here. So this becomes my new x. This becomes my new y. That's basically what we do. So my x-axis will be along the ramp. My y-axis will be perpendicular to the ramp, which means my normal force will be along this y direction, because the normal force is always perpendicular to the surface of contact. So let's look at the forces acting on this, or at least one force. I can definitely say that there is the Fg, the force of gravity. Okay. Now this angle here is theta. Now I'm going to break down this force into its x and y components. Now along the ramp is the x. Now I can look at the positive x direction as up or down, depending on which way the object is moving. If the object is moving up, up is positive, up the ramp. if the object is sliding down the ramp is positive. Now, and then I have my y-axis. Now, these two should be perpendicular. Maybe I didn't do a good job there. That's close. Okay. Now, this angle here, I can tell you that it's theta, and I'm not going to do like a formal geometry proof, but I'll show you quickly. If this is theta, let's just give it a number. It's 30. This is 90. This has to be 60. Now, between this dashed line and the ramp, that should be a 90-degree angle. They are perpendicular. So, which means this is 60, this has to be 30 to complete the 90. Okay, so I'm not going to do that again. So, it's always going to be like that. Now, any force that's not acting in the x or the y direction has to be resolved. All right, so for now, we should have a normal force that's always perpendicular to the ramp. Now I'm going to take this Fg and I'm going to split it. Now it has to be split into a component along the y direction and a component along the x direction. Okay. Now this component, this blue component here, has to be parallel to the x-axis because it's along the x direction. Okay. The other one has to be perpendicular because it's along the y direction. Well, since this is perpendicular to the ramp, I'm going to call it F perpendicular. The blue one, you guessed it, I'm going to call it F parallel. Or we can say FP. Okay? Now, this angle here, I hope you can see this, this angle here should be 90 degrees. So now I can write that FG is equal to, F perpendicular is Fg cosine of that angle. You can see that, I hope. You just put yourself inside this triangle here. Okay, F parallel is Fg sine theta. And Fg is equal to mass times acceleration of gravity. Now let's go back to what we talked about earlier. The F perpendicular, okay, has to equal to the normal force. And because this object does not move in the y direction, so I can say that Fn is equal to F perpendicular, right? And the other stuff we'll talk about later. Now let's see what happens to the normal force as the angle increases. Well, Fn is the same as F perpendicular, right? So this is Fn basically. If the angle increases, if you put this in your calculator, the cosine, okay, the cosine decreases, right? So as the angle increases, the cosine decreases, which means Fn has to decrease. If the angle increases, like I'm looking at this tendency to slide, this parallel force, or parallel component of Fg. If sine of theta, if theta increases, the sine of theta increases. You can do that. I'm not sure if you did that in the math, but you can put different angles into your calculator, and you can see that as the angle increases, the sine also increases. So I think the math supports what we talked about earlier. Now I'm going to try to do some special cases. Okay, because this might not be the only forces. Okay, now let's just look at a case where we have room here. Okay, case 1. Resting on the ramp. If you're resting on the ramp, okay, see, if you're resting on the ramp, it's got to be a force, okay, that's opposing F parallel, and it has to be equal in magnitude, and that force has to be friction. So it's got to be some friction here because the object has the tendency to go down the ramp, but something is preventing it. So this is the force of, actually, you know what, I'll call it lowercase f. So in this case here, the parallel force, okay, must equal to the force of friction. In other words, we're doing Newton's second law. So I'm going to look at down as positive. So basically, we're writing F parallel minus force of friction equals ma. Well, A is 0 because you're not moving. So that's why we end up with this. And at the same time, we have the normal force equals the F perpendicular, right? So let's see what we can do with this. So F parallel is equal to mu Fn. I'm using this. And Fn is just the, what do you call it? The perpendicular component, which is right here. And you can see that the perpendicular component is Fg cosine theta. So I'm going to write this as, well, Fg is also equal to mg. So a lot of substitutions here. Okay? And here, I can say that the parallel component is mg sine theta. So if you simplify this, you should get mu, this is static friction, equals tangent of theta. Okay? So if you want to find the coefficient of static friction, you just take the tangent of that angle. Now let's look at case 2. Let's say no friction. Okay, case 2. If there is no friction, this object has no choice but to accelerate, because the only force acting on it is the parallel force or parallel component of the weight, and it has no choice but to slide. So let's see if that what happens here. So I'm writing the sum of the forces equals ma along the ramp. So I'm going to choose down as positive because that's the way it's going to slide. It has to slide and accelerate. So F parallel equals ma. The parallel component is mg sine theta. It's up there. Equals m times a. Now I can cross out the masses, and I can see that the acceleration is just going to be g sine theta. On a frictionless ramp, the object will slide down, non-negotiable, and the acceleration will be 10 on Earth, basically, sine of this angle. So if this angle is 30, your acceleration will be 10 sine 30, which is 5 meters per second square. All right, let's just say case 3, I'm going to do friction. Let's just say accelerates down, acceleration plus friction. In other words, this parallel component is greater than the friction. So now we're dealing with the static, with the kinetic friction. So F parallel is bigger. So again, sum of the forces equals ma. I'm writing Newton's second law. All right, so it's got to be F parallel minus the force of friction equals ma. I hope you can see that. Okay, and you still have the other statement. This is going to be true all the time. No matter what you're doing, accelerating, not accelerating, it's always there. The parallel is mg sine theta, right? Minus the force of friction is mu Fn. And Fn is the perpendicular, and the perpendicular is Fg cosine theta, and Fg is mg. So I hope you can follow that. And this is equal to m times a. Okay, now you can manipulate this any way you want and find what you need, right? So basically, you have two statements. You have this one, and you do Newton's second law to come up with the other one. Okay. Let's just say case 4. Say once you get the idea, it's just a matter whether there is acceleration or no acceleration. Case 4, constant velocity with friction. So which means this force of friction has to equal the parallel force, and you're moving. So which means this becomes 0 basically, right? Because there is no acceleration, constant velocity. Let's look at other cases. So let's look at case 5. We're going to go constant velocity without friction. but this time we're going to be pulling up the ramp. Pulling or pushing up the ramp is the same thing. So now if we're going up the ramp, I'm going to change up as positive, and friction will no longer be there. Friction will be down here. And I'm applying a force. Maybe I'm using a rope. There's some tension in the rope. I'm pulling on the object. But there's definitely some applied force. Okay? And if I'm going at a constant velocity, the sum of friction and parallel component has to equal Fa. The combination of whatever is going down the ramp equals whatever is going up the ramp. So let's see how we can write this. Again, I'm going to write sum of the forces equals Ma. See, this does not change. That's going to stay there. Okay. So I think it's going to be Fa minus, so anything that's trying to make you go up the ramp, you take away whatever is holding you back. Well, since this is a constant velocity, the acceleration is 0, so this is going to be 0. Now, then you would manipulate this any way you want. Oh, I said no friction here. Okay, so let's just change that. So I'm going to say no friction, so it should look like this, right? If there is friction, you will just throw the friction in there because it's opposite the way you're traveling. Let's just say accelerating, okay, plus no friction. Okay, so if there's no friction, this will go away, but this will not be 0. It will be m times a. If there is friction and it's accelerating, it will be Fa minus F parallel equals Ma. So there are a lot of cases, right? But the concept is the same. It's basically Newton's second law along the ramp, right? And in this direction, perpendicular to the ramp, is going to be Fn equal to F perpendicular at all times because we're not pulling or pushing at an angle on the ramp. In other words, this force is not making an angle with the ramp, which can make things a little bit difficult. All right, and that's it. I will do more problems in class, and that should do it. All right, I'm out. Peace.